What if everything you know, every star, every galaxy, even the very fabric of reality itself, could disappear in less time than it takes to blink? Picture this: one moment, the universe hums along as it always has, and the next, nothing. No light, no matter, no space, just an infinite, silent void where existence once was. This isn't science fiction. It's a chilling possibility rooted in the laws of physics, a phenomenon known as vacuum decay. At the quantum level, our universe might be balancing on a knife's edge, and the wrong shift could unravel everything in an instant. The idea sounds like something from the darkest corners of theoretical physics, but it's grounded in real science. Imagine the universe as a fragile bubble suspended in a vast, unseen cosmic foam. Inside our bubble, the rules of physics are stable. Gravity holds planets in orbit, light travels at a constant speed, and time marches forward. But outside, there could be other bubbles, other universes with entirely different laws. And if our bubble pops, if the quantum field holding reality together suddenly collapses, the domino effect would be unstoppable. A wave of destruction would race outward at the speed of light, rewriting the fundamental nature of existence itself. By the time we saw it coming, it would already be too late. So why hasn't this happened yet? And if the risk is real, how close are we to the edge? The answers lie in the strange, counterintuitive world of quantum mechanics, where particles flicker in and out of existence and empty space is anything but empty. Over the next few minutes, we'll explore how vacuum decay could rewrite the cosmos, why some scientists take the threat seriously, and whether there's anything we could do to stop it. This isn't just a theoretical curiosity, it's a window into the deepest mysteries of reality, a reminder of how little we truly understand about the universe we call home. Buckle up, we're about to dive into one of the most mind-bending concepts physics has ever conceived. To grasp how vacuum decay could erase reality, we need to start with something invisible yet everywhere: quantum fields. Think of them as an endless, invisible ocean stretching across the entire universe. Just like waves ripple across water, particles, electrons, quarks, even light itself are just tiny disturbances in these fields. The chair you're sitting on, a pattern of vibrations in the electron field. The screen in front of you ripples in the electromagnetic field. Everything we consider real is just energy dancing atop this hidden cosmic fabric. But here's where it gets eerie. These fields aren't static, they're more like a restless sea, constantly churning with fluctuations at the smallest scales. Even in what we call empty space, particles briefly flicker in and out of existence, borrowing energy from the fields before vanishing again. It's as if the universe is never truly at rest, and that instability holds the key to vacuum decay. Picture blowing soap bubbles. Most float peacefully, but every so often one pops unexpectedly. The universe might be just as fragile. Scientists describe this using the idea of false vacuum. Imagine balancing a marble on the edge of a salad bowl. It might sit there for years, seemingly stable, but the slightest nudge sends it crashing to the bottom. Our universe could be that marble perched on a precarious ledge. The quantum fields holding everything together might not be in their lowest possible energy state. If they suddenly drop to a truer, more stable level, the rules of physics as we know them would rewrite instantly. Atoms would unravel, forces would cease to function, and the universe as we know it would vanish without warning. This isn't just speculative doom-mongering. The math behind it comes from the same equations that predict the behavior of particles in laboratories. The Higgs field, the quantum field responsible for giving particles mass, could be a prime suspect. In 2012, the discovery of the Higgs boson confirmed this field's existence, but it also raised a haunting question. Is it stable, or are we living on borrowed time? Some calculations suggest the Higgs field might be metastable, like a skyscraper swaying gently in the wind. For now, it holds, but under the right conditions. The whole structure could collapse. The Higgs field isn't just another invisible force in the universe, it's the cosmic architect behind mass itself. Without it, particles would zip around at the speed of light, never clumping together to form atoms, planets, or people. Think of it as the universe's ultimate glue, quietly shaping everything from the tiniest quark to the largest galaxy. But this essential field might also be hiding a dangerous secret. Right now, it could be in a state physicists call metastable. Picture balancing a pencil perfectly on its tip. For a fleeting moment, it stands upright, defying gravity. But the slightest vibration, a breath of air, a distant footstep sends it toppling. The Higgs field might be in a similar precarious balance. Mathematical models suggest it's not sitting at the lowest possible energy state, the universe's most stable configuration. Instead, it's perched somewhere higher, like a marble resting on a ledge halfway down a hill, stable for now, but one nudge away from rolling into the abyss. What could provide that nudge? Quantum fluctuations, the same tiny, random bursts of energy that make empty space seethe with virtual particles. Most of these fluctuations cancel out harmlessly, but in theory, one could be just large enough to tip the Higgs field into a lower energy state. If that happened, the effects would cascade at the speed of light. The laws of physics as we know them would rewrite themselves, atoms would dissolve. Forces like electromagnetism and the strong nuclear force could vanish or transform beyond recognition. The universe wouldn't just end with a bang or a whimper, it would end with a fundamental redefinition of reality itself. Here's the unsettling part: we wouldn't see it coming. The change would spread like a shockwave, and by the time it reached us, there'd be no time to react. One moment, everything's normal. The next, the very rules holding existence together have changed. Some theories even suggest this might have already happened elsewhere in the cosmos, that beyond our observable universe, entire regions could have succumbed to vacuum decay, their physics erased and replaced by something entirely alien. Yet despite this eerie possibility, the Higgs field has held steady for over 13 billion years. That longevity offers a sliver of reassurance. Either the field is more stable than we think, or the odds of a catastrophic fluctuation are vanishingly small. Scientists continue to refine their calculations, probing the Higgs boson's properties for clues. Every new measurement at particle colliders like the Large Hadron Collider could inch us closer to understanding whether we're living on a cosmic tightrope or standing on solid ground. So while vacuum decay remains a terrifying hypothetical, it's also a reminder of how much we still don't know about the quantum underpinnings of reality. The Higgs field isn't just a scientific curiosity, it's a silent guardian of the universe's stability, and its mysteries might hold the answer to whether our cosmic bubble pops tomorrow or lasts for eternity. If our universe is a car parked on a steep hill with the parking brake barely holding, the false vacuum is that uneasy moment before the vehicle starts rolling, the current state where things seem stable but only just. This precarious balance defines our cosmic reality. The false vacuum isn't the lowest energy state possible. It's more like a temporary ledge halfway down a mountain. The quantum fields that dictate the behavior of particles, the same fields that give rise to atoms, light, and the forces we know, are frozen in a suboptimal configuration. They're stuck like a ball trapped in a dip on the hillside, not yet settled at the bottom. Now imagine the true vacuum, the bottom of the valley where the ball finally comes to rest. In this state, quantum fields would settle into their lowest possible energy, rewriting the fundamental laws of physics. The universe wouldn't just change, it would reset. The forces that bind atoms, the speed of light, even the concept of mass might vanish or morph into something unrecognizable. It would be like replacing the rules of chess mid-game, only to realize the new game has no pieces, no board, and no players. Here's the catch: if the universe transitioned to a true vacuum, the effects wouldn't just alter a corner of space. they'd spread outward at light speed, erasing the old physics in their wake. Picture a wave crashing through the cosmos, not destroying matter but redefining what matter even means. Stars wouldn't explode, they'd simply cease to function, their atomic structures unraveling as electromagnetism and the nuclear forces dissolved. Life, planets, galaxies, none would have a chance. The universe wouldn't end with fire or ice, but with a quiet, absolute reconfiguration, and yet we're still here. The fact that we exist suggests the false vacuum is stable enough to last billions of years, or that we're phenomenally lucky. Some theories propose that the Higgs field's metastability is like a mountain with two valleys. Ours is higher, but the drop to the lower one is so steep that quantum fluctuations rarely provide enough energy to kick the ball over the ridge. That's why vacuum decay hasn't happened yet, but if it ever does, the transition would be unstoppable, irreversible, and utterly indifferent to the civilization it erases. So why does any of this matter? Because the universe's fragility forces us to confront how little we truly control and how much we still have to learn. Every particle collision in accelerators like the Large Hadron Collider peels back another layer of the quantum world, testing whether our cosmic hillside is eroding or if we're standing on bedrock. The difference between a false vacuum and a true one might be the difference between existence and oblivion, and that's a valley we'd rather never reach. The scariest part about vacuum decay isn't just that it could happen, it's how absurdly simple the trigger might be. All it would take is one tiny quantum fluctuation, a random blip in the energy of empty space, to set off a chain reaction with cosmic consequences. Imagine lighting a match in a dry forest. A single spark under the right conditions can ignite an unstoppable wildfire. Now replace the forest with the fabric of reality, and the match with a particle collision or a random energy spike. That's the terrifying simplicity of how vacuum decay could begin. At the quantum level, empty space isn't truly empty. It's a seething, frothing sea of potential, where particles and antiparticles constantly pop in and out of existence. Most of these fluctuations cancel each other out in an instant, vanishing without a trace. But every so often, one might carry just enough energy to nudge the Higgs field, or another quantum field, over the edge. Think of it like shaking a soda can. Most of the time, nothing happens. But if you shake it hard enough at just the right angle, the pressure inside becomes too much and the can bursts open. In this case, the soda is the false vacuum, and the burst is a bubble of true vacuum expanding at the speed of light. High-energy events could also act as triggers. Particle colliders like the Large Hadron Collider smash protons together at nearly the speed of light, recreating conditions that haven't existed since the Big Bang. Some have worried these experiments might accidentally create a bubble of true vacuum, though the consensus is that the energy levels involved are far too low to pose a real risk. But nature itself produces far more violent collisions. Cosmic rays, high-energy particles from deep space, routinely slam into Earth's atmosphere with energies far beyond anything we can create in a lab. A chance collision in just the right way, in just the right place, could theoretically be the spark that starts the fire. Once that bubble forms, the rules change literally. The boundary between the false vacuum and the true vacuum would act like a wall of annihilation, not destroying matter but redefining it. Every atom, every force, every fundamental constant we rely on would cease to function as before. And because this bubble expands at light speed, there'd be no warning. One moment, physics works the way we expect, the next it doesn't. The universe wouldn't end with a bang or a whimper, but with a silent rewrite of its own rulebook. Entire galaxies could vanish not in fire or ice, but in a quiet, unstoppable wave of something else. Something we can't even imagine, because the very laws allowing us to imagine would be gone. Yet for all its horror, the odds of this happening are vanishingly small. The universe has lasted over 13 billion years without collapsing, a pretty good track record. But the fact that it's even possible forces us to confront just how delicate the cosmic balance really is. We're not just living in the universe, we're living on its knife's edge. Once that bubble of true vacuum forms, the rewriting of reality begins, and it spreads faster than anything in the universe can outrun. Traveling at the speed of light, this boundary wouldn't just erase stars or planets, it would dismantle the very framework that allows them to exist. Picture a drop of ink falling into a glass of water, spreading inexorably until every last molecule is stained. Except here, the ink isn't changing the color of the cosmos, it's deleting the rules that define color itself. The bubble's edge would be a wall of transformation, a shockwave where the old physics shatter and the new, unknown laws take hold. Atoms caught in its path wouldn't explode or collapse, they'd simply stop being atoms. The forces that bind their nuclei, the electrons zipping around them, all of it would reconfigure into something else, something alien to everything we know. And because this wave moves at light speed, no signal, no warning flash could outpace it. The first glimpse of the bubble would be the moment it arrives. By the time you saw the darkness coming, you'd already be inside it. There's no hiding, no escaping to some distant corner of the universe. Light speed is the ultimate speed limit. Nothing travels faster, not information, not gravity, not even panic. A civilization with the most advanced technology imaginable would have zero chance to react. One instant, their scientists might detect an anomaly at the edge of their observable universe. The next, their instruments and the scientists themselves would cease to function as the bubble washed over them. Entire galaxies would blink out of existence, not with fireworks, but with a quiet, fundamental shift, like a computer program overwritten by new code. What makes this unstoppable isn't just the speed, it's the totality of the change. Unlike a supernova or a black hole, which twist spacetime but leave the rules intact, vacuum decay doesn't destroy. It replaces. The universe wouldn't end, it would become something else entirely, a place where concepts like matter, energy, or life might no longer apply. Imagine trying to play a symphony after someone replaced every note in the musical scale. The instruments are still there, but the music, the thing that made them meaningful, is gone. And here's the cruel irony. Even if we saw the bubble forming in some distant galaxy, we'd never know what was inside. The light from the transformed region would carry no information about its new laws. It would be like staring at a black hole's event horizon, but worse, because beyond that boundary, physics itself might not even allow light to exist. The bubble wouldn't just be a death sentence for our universe, it would be the ultimate cosmic silence. Yet for all its horror, this scenario reveals something profound about reality. The laws we take for granted, gravity pulling us to Earth, the sun warming our skin, aren't just rules. They're a fragile arrangement, a temporary agreement between quantum fields. The universe isn't just vast, it's volatile, balanced on a knife's edge between stability and oblivion. Every second we exist is a second that the dice haven't rolled against us. And that's a reminder to cherish the physics we have, because out there, in the infinite dark, the rules could be very different, and one day they might be. One instant you're here, breathing, thinking, alive. The next you're not. Not gone in the way a supernova obliterates a planet, not vanished like matter sucked into a black hole. This is something far stranger. As the true vacuum bubble sweeps through, the atoms in your body wouldn't explode or crumble. They'd simply stop being atoms. The electrons orbiting nuclei gone or rewritten into something unrecognizable. The forces holding your molecules together erased, as if the universe forgot how to play by its own rules. There'd be no pain, no panic, no flicker of awareness. Just an unfathomable shift, like a light switched off in a room that never existed. Stars wouldn't flare or collapse. They'd wink out mid-fusion, their fiery hearts no longer bound by the laws that made them burn. Galaxies would dissolve not with a roar, but with a silent, flawless reconfiguration. even spacetime itself, the invisible fabric stretching the cosmos, might unravel or twist into a new geometry. Gravity, light, causality, all the pillars of reality, could melt away or morph into forms beyond human comprehension. It wouldn't be destruction in the traditional sense. More like the universe pressing a cosmic reset button, one that doesn't just clear the data but reprograms the hardware, and the cruelest part, you'd never see it coming. The bubble expands at light speed, meaning the first sign of its arrival is its arrival. By the time your eyes could process the wave fronted, if eyes even still function in that fleeting nanosecond, it would already be rewriting the neurons in your brain. No time to scream, to react, to say goodbye, just an unfathomable cutoff, as if existence itself had been a simulation and someone abruptly changed the code. This is the haunting paradox of vacuum decay. It's not violent but absolute, not an end but a transformation so total that concepts like end or beginning might no longer apply. The universe wouldn't die, it would become something else entirely, a place where the word universe no longer fits. And we, along with every galaxy, every black hole, every lingering echo of the Big Bang, would slip silently into that unknowable new normal. No drama, no fanfare, just physics itself turning the page to a blank chapter. The scale of vacuum decay's devastation isn't just planetary or galactic, it's cosmic. Every star, every black hole, every distant quasar pulsing with ancient light would vanish as suddenly as a candle snuffed in the wind. This isn't an extinction event, it's the erasure of the very stage on which existence plays out. Imagine a library where every book isn't burned but unmade, the ink, the pages, even the idea of words dissolving into nothingness. That's the magnitude of what vacuum decay would do to the universe. Consider the observable universe, that vast sphere of space stretching nearly 93 billion light-years across. Within it, an estimated 2 trillion galaxies spin, each home to billions of stars. Civilizations might rise and fall on distant worlds, their stories forever untold. Art, science, love. Entire histories could flicker out in an instant, not with destruction but with redefinition. The bubble of true vacuum wouldn't discriminate between a hummingbird's wingbeat and the slow death of a red giant star. Both would cease to function under the new, alien physics, their forms unraveling like knots in a rope cut loose. Even black holes, those titanic traps where gravity bends spacetime into oblivion, wouldn't be spared. Their immense pull relies on the rules of general relativity. But if vacuum decay rewrote those rules, their event horizons might simply dissolve. The singularity at their core, infinitely dense, infinitely small, could blink out like a glitch in the cosmos's code, and the light from stars that took billions of years to reach us. Gone mid-journey as the photons carrying it ceased to be light in any recognizable sense. The most haunting thought isn't the loss of matter or energy, it's the loss of possibility. Every unhatched idea, every undiscovered species on distant exoplanets, every future Beethoven or Einstein born under an alien sun, erased not by catastrophe but by a silent change in the universe's operating system. Vacuum decay wouldn't just end life, it would end the potential for life forever. The cosmic clock wouldn't just stop, it would melt. Yet there's a strange comfort in this terrifying scenario. The fact that it hasn't happened yet suggests the universe is staggeringly stable, or that we're perched in a sweet spot of cosmic longevity. Either way, it's a reminder that reality, for all its fragility, has held firm for billions of years. The stars still shine, the atoms in your body still cling together, and the laws of physics remain mercifully consistent. For now, the bubble hasn't formed. For now, the universe endures, and that's enough. The terrifying truth about vacuum decay is that it doesn't operate on a human timescale or any timescale at all. It could take a googol years, that's a 1 followed by 100 zeros, or it could happen before you finish this sentence. Quantum physics doesn't care about our calendars or cosmic schedules. It runs on probability, not predictability. Picture rolling a die with an infinite number of sides. Most land harmlessly, but somewhere in that sea of possibilities is the one roll that changes everything. What makes this so unsettling is the sheer randomness. We're used to threats with warning signs, asteroids we can track, supervolcanoes that rumble before erupting. But vacuum decay doesn't announce itself. It's not like a time bomb ticking down. It's more like a light switch that could flip at any moment for no reason at all. The trigger could be a random quantum fluctuation in deep space, a high-energy cosmic ray collision, or even, in theory, an unnoticed blip in a particle accelerator. The universe doesn't need a reason. It just needs the right or wrong roll of the quantum dice. Here's where probability becomes both our comfort and our curse. The math suggests the odds of decay happening in any given year are astronomically low. So low, in fact, that the universe could last trillions of times its current age before the dice land wrong. But probability isn't promise. It doesn't guarantee safety, only likelihood. Think of it like walking across a frozen lake. The ice might hold for 1,000 crossings until the one time it doesn't. The longer you walk, the more chances there are for the ice to crack. But that crack could happen on step 1 or step 1,000,000. This isn't just philosophical musing. Quantum fields are constantly in flux, and their behavior hinges on statistics, not certainty. The Higgs field, for instance, has a half-life, a point where the probability of decay reaches 50%. Some models place that half-life at around 10 to the power of 100 years. That's such an absurdly large number, it dwarfs the age of the universe by orders of magnitude. But here's the catch: half-life doesn't mean safe until then. It just means the coin flips from probably won't happen to probably will over unthinkable eons. The first flip could land tails tomorrow. What's truly humbling is how powerless we are against this uncertainty. Humanity has tamed earthquakes, diverted asteroids, and cured diseases, but we can't negotiate with quantum fields. There's no early warning system, no cosmic fuse to cut. If the Higgs field tips tonight, we'll never know. The change would arrive at light speed, rewriting reality before our neurons could fire a final thought. Yet there's a strange relief in accepting this. The universe doesn't keep us in suspense. It doesn't drag out the inevitable. If decay comes, it will be instant, absolute, and utterly indifferent. No panic, no countdown, just a silent transition from one set of physical laws to another. And until then, the dice keep rolling, the ice holds, the universe hums along, blissfully unaware of its own fragility. By the time we realized vacuum decay had begun, it would already be rewriting the atoms in our eyes. There'd be no warning shot, no distant flicker on a telescope, just an impossible split second where the universe's rules unravel at light speed. Imagine standing in a pitch-black room when someone suddenly flips on a lamp. The moment you perceive the light is the moment it touches you. Now replace the lamp with an unstoppable wall of redefined physics and the darkness with oblivion. That's the brutal efficiency of vacuum decay. The problem isn't just speed, it's information. For us to detect something, whether a supernova or an asteroid, it must send a signal we can intercept. Light, gravity waves, or some other ripple in the fabric of space. But the true vacuum bubble wouldn't broadcast its approach. It would be the signal rewriting the laws that govern signals themselves. Think of it like a silent alarm that doesn't just alert you to danger, it erases your ability to hear alarms. By the time instruments registered anything anomalous, they'd already be malfunctioning, their circuitry governed by new, alien physics. Even if we somehow spotted the bubble forming in a distant galaxy, a sudden patch of darkness where stars winked out, we'd learn nothing useful. The light reaching us from that region would show only the last moments of the old physics, like a final scream echoing from a collapsing mine, the bubble's interior. A blank spot in reality. No data could escape the transition because information itself would be subject to the new rules. It's like trying to study the inside of a black hole using telescopes. The event horizon doesn't just hide things, it breaks the very tools we'd use to observe it. This isn't a failure of technology or imagination. It's a fundamental limit baked into the universe. Causality, the rule that effects follow causes, relies on the stability of physics. But vacuum decay doesn't play by those rules, it changes them mid-game. A civilization could build detectors spanning solar systems, monitoring every quantum fluctuation, and still be blindsided. The only early warning would be statistical, calculating the infinitesimal chance that decay might happen in our cosmic neighborhood. Not helpful when the consequence is instant and universal. Some theories suggest rare quantum effects might allow microscopic true vacuum bubbles to form briefly before fizzling out. If we could detect those, perhaps we'd glimpse the threat in advance, but here's the catch: such bubbles would be indistinguishable from background quantum noise. It's like trying to spot a single melting snowflake in a blizzard. Even if we knew what to look for, nature drowns the signal in chaos, and that's the cruelest twist. The universe hides its own reset button in plain sight. The very forces that let us build telescopes and satellites, the consistency of electromagnetism, the reliability of light, would betray us in the end. The first and only sign of vacuum decay would be its arrival, an absolute silent cutoff where the rules we trust dissolve without a trace, no countdown, no farewell. Just physics itself pressing delete. Vacuum decay isn't the stuff of sci-fi explosions or cosmic monsters. It's far stranger and more subtle than that. Hollywood loves to depict the end of the universe as a black hole swallowing everything or antimatter annihilating matter in a spectacular blaze. But vacuum decay doesn't play by those rules. It's not a collision or a collapse. It's a quiet, fundamental rewrite of reality's code. Let's untangle the myths and zero in on what this phenomenon really is and what it isn't. First, black holes have nothing to do with it. These gravitational beasts are terrifying in their own right, crushing stars into singularity and warping spacetime beyond recognition. But they're still bound by the same physics as the rest of the universe. Vacuum decay, on the other hand, changes those physics. A black hole might bend the rules, but vacuum decay throws out the rulebook entirely. Even the mightiest black hole would dissolve without a trace if a true vacuum bubble washed over it, because the very concept of singularity might no longer apply under the new laws. Then there's antimatter, the mirror image of normal matter that annihilates on contact with it, releasing energy in a burst of gamma rays. Antimatter is dramatic, but it's still just matter playing by the universe's existing rules. Vacuum decay isn't about particles meeting their opposites, it's about the stage itself being ripped away. Imagine a play where the actors suddenly forget their lines versus one where the theater vanishes mid-scene. Antimatter is the former, vacuum decay is the latter, another common mix-up, confusing vacuum decay with the big crunch or heat death of the universe. Those are classic in-game scenarios, the universe either collapsing back into a singularity or fading into a cold, lifeless expanse. Both rely on gravity and thermodynamics, the same forces we understand today. Vacuum decay doesn't wait for stars to burn out or galaxies to merge. It could strike at any moment, overriding gravity, thermodynamics, and every other force in an instant. Even the term decay is misleading. It's not a slow rot or erosion like a dying star or rusting metal. It's a sudden, all-at-once shift like flipping a switch. The quantum fields that govern reality don't crumble, they snap into a new state, taking everything else with them. A better metaphor might be a software update, except this one doesn't ask for permission or warn you about the changes. The universe just reboots and the old operating system never comes back online. So why do these misconceptions persist? Because our brains struggle with the sheer abstraction of vacuum decay. Destruction, we understand explosions, collisions, things breaking apart. but the idea that existence itself could reconfigure into something unknowable. That's harder to picture. We default to familiar tropes even when they don't fit. The truth is, vacuum decay isn't like anything we've seen or imagined. It's not a disaster movie, it's a cosmic edit button, and once pressed, there's no undo. This isn't just splitting hairs, it's about grasping the true scale of the threat. Black holes and antimatter are localized dangers. Vacuum decay is universal, instant, and absolute. It doesn't leave ruins behind because ruins imply remnants of the old rules. Instead, it erases the foundation those ruins would stand on. The universe wouldn't end with a bang, a whimper, or even a whisper. It would end with a silent, irreversible refresh, one we'd never see coming. Science fiction has imagined countless ways the universe could end. Black holes run amok, alien superweapons, rogue planets on collision courses. But for all their creativity, even the wildest fictional doomsdays pale in comparison to the eerie simplicity of vacuum decay. Take Doctor Who's The Pandorica Opens, where every star in the sky winks out simultaneously, an event the show attributes to a temporal explosion. Visually stunning, but still bound by familiar physics, stars vanishing implies something destroyed them. Vacuum decay doesn't bother with destruction. It doesn't remove stars, it redefines what a star is. No explosion, no debris, just a silent, universal edit where the concept of star no longer applies. Or consider The Hitchhiker's Guide to the Galaxy, where the Earth is demolished for a galactic highway. Absurd, absolutely, but at least there's paperwork. Bureaucrats file notices, construction crews show up, it's an ending with process. Vacuum decay offers no such ceremony, no permits, no warning signs. Just a quantum fluctuation so small it defies measurement, triggering a wave of reconfiguration that respects no authority, no appeals, no last-minute heroics. Fiction loves protagonists who outthink doom, scientists recalculating trajectories, rebels hacking mainframes. Against vacuum decay, there's no algorithm to hack, no countdown to pause. The universe doesn't negotiate. Even the Matrix's system-wide reboot feels quaint next to real physics. When Neo resets the simulation, the rules stay intact, humans still breathe, bullets still fly. Vacuum decay wouldn't just restart the simulation, it would delete the programming language. Imagine logging into your computer to find the keyboard now controls smell instead of letters. That's the level of incomprehensible shift we're talking about. What makes these fictional apocalypses comforting is their tangibility. We understand black holes swallowing planets or asteroids striking Earth. But vacuum decay operates on a scale so abstract it challenges storytelling itself. How do you dramatize a villain that isn't a thing but a statistical inevitability? How do you depict a catastrophe that isn't loud or violent but surgically precise in its erasure of physics? No wonder screenwriters avoid it. It's not just terrifying. It's inconceivable. Yet here's the twist: reality doesn't need drama to be horrifying. The utter indifference of vacuum decay, its lack of malice, spectacle, or logic, is what makes it uniquely chilling. Fictional doomsdays entertain, real physics humbles, and in that humility there's a strange beauty. The universe's end might not be a story at all, just a footnote in the quantum ledger written in vanishing ink. The idea that reality itself could unravel didn't spring from ancient mythology or apocalyptic fiction. It emerged from the quiet calculations of 20th century physicists grappling with quantum fields. In the 1970s, scientists began questioning a fundamental assumption. What if the universe isn't in its most stable possible state? Harvard physicist Sidney Coleman became central to this unsettling revelation. Alongside his collaborator Frank DeLucia, he published a groundbreaking paper in 1980 titled Gravitational Effects on and of Vacuum Decay, turning abstract quantum theory into a chilling cosmic possibility. Their work built on earlier discoveries about quantum fields, the invisible scaffolding beneath particles and forces. But Coleman took it further, calculating how these fields might transition from higher energy states to lower ones through a process called bubble nucleation. Imagine a pot of water heated just below boiling. It looks calm, but tiny vapor bubbles constantly form and collapse beneath the surface. Most vanish instantly, but given enough time, one grows large enough to trigger a full boil. Coleman's math suggested the universe behaves similarly, with quantum fluctuations occasionally forming microscopic bubbles of true vacuum. Most would fizzle out harmlessly, but one, under the right conditions, could expand uncontrollably. This wasn't just speculation. Coleman's equations showed that if such a bubble formed, its walls would accelerate outward at nearly light speed, propelled by the energy difference between the false vacuum outside and the true vacuum inside. The math was elegant, the implications horrifying. For the first time, theoretical physics had outlined a mechanism by which reality could rewrite itself without warning. The universe wouldn't end with a bang or a whimper, but with a silent, perfect reconfiguration, an idea so radical it sounded like science fiction, yet emerged from rigorous mathematics. These calculations didn't happen in isolation. They grew from decades of quantum research, from Paul Dirac's early field theories to Julian Schwinger's work on quantum electrodynamics. But Coleman's contribution was pivotal because it bridged abstract quantum mechanics with existential risk. Before him, physicists debated whether the vacuum state was stable. After him, they had to confront the possibility that we're all living on borrowed time in a cosmic house of cards. What's striking is how calmly the scientific community absorbed these apocalyptic implications. Physics journals filled with discussions of bubble nucleation rates and tunneling probabilities, treating the potential annihilation of reality as just another variable to solve for. Coleman himself had a wry humor about it, once quipping that if vacuum decay occurred, not only wouldn't you get to publish your next paper, neither would anyone else. The gallows humor masked a profound philosophical shift. Humanity now had mathematical proof that existence might be far more fragile than anyone imagined. This theoretical framework didn't just predict doom, it reshaped how physicists viewed quantum fields. Suddenly, the Higgs field wasn't just a mechanism for mass, it was a potential ticking time bomb. Subsequent researchers like Stephen Hawking and Leonard Susskind grappled with these ideas, weaving them into wider theories about multiverses and cosmic inflation. The unsettling truth was that our universe might be one bubble among countless others in a frothing quantum foam, each with different physical laws. Some might be more stable, others could have already decayed. We might simply be in a bubble that hasn't popped. Yet, today, Coleman's work remains foundational to our understanding of vacuum metastability. Modern particle colliders like the Large Hadron Collider probe the Higgs field's properties, searching for clues about its long-term stability. Each experiment inches us closer to answering whether we're living in a cosmic accident waiting to correct itself, or a universe built to last. The equations scribbled in 1970s notebooks didn't just solve abstract problems. They revealed that reality's fragility isn't poetry, it's physics. When scientists first powered up the Large Hadron Collider, a whisper of unease spread through the public. Could smashing protons together at nearly light speed trigger an unstoppable chain reaction? It's a fair question after all. We're recreating conditions unseen since the Big Bang. But here's the reassuring reality. Nature has already run this experiment countless times, and we're still here. Every second, Earth's atmosphere is bombarded by cosmic rays particles from deep space that collide with molecules overhead at energies far exceeding anything our puny particle colliders can muster. Some of these cosmic impacts pack over 100 million times the energy of the LHC's most powerful collisions. If high-energy events could spark vacuum decay, it would have happened long ago, sparked by random cosmic fireworks rather than human tinkering. The universe, it seems, has built-in safeguards far beyond our laboratories. That's not to say researchers didn't take the concern seriously. Before the LHC's launch, teams of physicists conducted exhaustive safety reviews examining every conceivable doomsday scenario. Their conclusions were unanimous. The energies involved in human-made collisions are laughably small compared to what's needed to destabilize the quantum vacuum. Think of it like striking a match next to a volcano. Nature's raw power dwarfs anything we could produce. The math behind this safety margin comes down to scale. To potentially disturb the Higgs field's metastability, you'd need energies approaching the Planck scale, 10 to the power of 19 gigaelectronvolts. That's a 1 followed by 19 zeros. The LHC, by comparison, operates at a mere 13 teraelectronvolts. It's the difference between tossing pebbles into a pond and trying to drain the ocean with a teaspoon. Even if we built a collider encircling the entire planet, we'd still fall orders of magnitude short of the danger zone. There's a deeper irony here. The same cosmic rays that occasionally trigger vacuum decay, in theory, also serve as our cosmic canary in the coal mine. If high-energy collisions were truly risky, the universe would have reset itself eons ago. Instead, we observe ancient light from galaxies billions of light-years away, proof that vacuum decay hasn't erased those regions yet. Every photon that reaches us from the distant cosmos is effectively a safety certificate, signed by nature itself. This doesn't mean vacuum decay is impossible, just that human activity isn't tipping the scales. The real threat, if it exists, comes from random quantum fluctuations or cosmic events we can't control or predict. Particle accelerators are less like apocalyptic triggers and more like microscopes for the quantum world, letting us glimpse the universe's underlying rules without shaking its foundations. So while the LHC might not destroy reality, it has revealed something equally profound, just how precariously balanced that reality might be. Our experiments haven't found evidence that the Higgs field is on the brink of collapse, but they have confirmed we're living in a universe where such questions aren't just philosophical. They're measurable, and that knowledge alone changes how we see our place in the cosmos. Here's a thought that might send shivers down your spine. If vacuum decay were even remotely probable, we wouldn't be here to worry about it. This unsettling realization forms the backbone of what physicists call the anthropic principle, a philosophical twist that turns our very existence into a cosmic clue. The logic is brutally simple. If the universe were prone to sudden, spontaneous collapse, life capable of observing it would never have had time to evolve. The fact that we're here staring at the stars and pondering quantum doom suggests something profound about the stability of reality, but does that mean we're safe? Not necessarily. The anthropic principle isn't a guarantee, it's a statistical observation. Imagine playing Russian roulette with 100 chambers and only one bullet. If you pull the trigger and survive, you might conclude the gun was mostly empty, but that doesn't change the fact that the bullet was still in there waiting. Similarly, our universe could be one of countless others where decay happened instantly, leaving no observers behind. We're just the lucky ones who rolled the cosmic dice and got to keep playing. This idea branches into even wilder territory when you consider multiverse theories. If infinite universes exist with varying physical laws, most might be unstable, popping like soap bubbles shortly after forming. A handful like ours could linger long enough for galaxies, planets, and curious minds to emerge. In this view, vacuum decay isn't just unlikely, it's already happened everywhere else. We're not special, we're survivors, yet there's another possibility, one that's harder to swallow. What if we're missing something fundamental? The anthropic principle assumes our current understanding of quantum fields is complete, but history shows physics is full of blind spots. Before the 20th century, no one imagined atoms could split, spacetime could bend, or empty space could teem with virtual particles. Could there be some hidden mechanism, a cosmic failsafe, that prevents vacuum decay altogether? Maybe the Higgs field is more stable than our equations suggest, or perhaps there's an undiscovered force acting as a quantum watchdog, keeping reality in check. For now, all we have are probabilities and philosophical puzzles. The universe has lasted 13.8 billion years without collapsing, which is either a reassuring trend or the longest streak of luck in history. Either way, it's a humbling reminder that our existence isn't just a product of physics, it's a filter for it. The laws we take for granted might not be the only possible laws. They're just the ones that didn't erase us before we could take notes. If our bubble of reality popped, would the infection spread? The terrifying possibility of vacuum decay doesn't just threaten our universe, it raises an even larger question. In a multiverse teeming with countless other cosmic bubbles, could this unraveling jump the gap between worlds? Imagine a row of dominoes, each representing a separate universe with its own unique physics. If one domino falls, does the entire line topple, or are these cosmic pockets isolated enough to escape the contagion? The answer hinges on an even deeper mystery: how separate these universes truly are. Some theories suggest the multiverse is a frothing quantum foam, with new bubbles constantly budding off from old ones, all floating in an even vaster metaspace. If that's the case, the walls between universes might be impenetrable. A true vacuum bubble forming in our universe would expand at light speed, but if it hit the boundary of our cosmic pocket, it could simply stop. Like a flame running out of oxygen at the edge of a sealed jar, other universes would remain untouched, their physics intact, their civilizations blissfully unaware of our silent erasure. But there's a darker scenario. If the space between universes isn't a true barrier, if it's more like a shared substrate, a cosmic superhighway connecting all bubbles, then vacuum decay might not respect borders. A true vacuum could, in theory, tunnel through the multiverse's scaffolding, rewriting reality after reality in an unstoppable wave. Picture a computer virus leaping from one isolated server to another through a hidden network cable. Once the infection starts, no backup is safe. Here's where the math gets speculative. Some models suggest that if a true vacuum forms, the energy released at its boundary could warp spacetime so violently, it might create new quantum tunnels to other universes. It wouldn't just destroy, it would multiply, branching out like fractal lightning. In this nightmare version of the multiverse, one collapse could trigger a chain reaction, turning the cosmos into a ticking time bomb where each detonation births more explosions. Yet there's a counter-argument buried in the physics. If other universes operate under fundamentally different laws, if their quantum fields aren't even shaped like ours, then our version of vacuum decay might be meaningless there. Think of it like trying to burn water. Fire relies on specific chemical rules. Change those rules and combustion becomes impossible. A true vacuum in our universe might fizzle out at the border of a universe where vacuum doesn't function the same way. For now, these ideas live in the realm of theory, but they're not pure fantasy. When physicists analyze vacuum decay, they're forced to confront questions about the larger multiverse structure. The same equations that predict bubble nucleation in our universe can be stretched tentatively to model how such bubbles might interact with other realities. The results are inconclusive, but the implications are staggering. We could be living in a cosmic archipelago where each island is quarantined from disaster, or in a house of cards where one falling card brings down the whole stack. The unsettling truth is this: if the multiverse exists, it might not offer safety in numbers. Those other universes could be just as fragile as ours, their existence balanced on the same quantum knife edge. Or they might be fortresses, their physics engineered to resist any decay. We won't know until we understand the deeper architecture of reality, assuming it doesn't rewrite itself first. If the universe truly hangs by a quantum thread, how much should humanity know, or not know, about its fragility? This isn't just theoretical physics anymore, it's an ethical minefield. Picture a team of researchers huddled over data that suggests the Higgs field is more unstable than previously thought. Do they publish their findings, risking global anxiety over something no one can control? Or do they bury the results, trading transparency for temporary peace? There's no easy answer, only shades of moral gray. History offers unsettling parallels. When scientists discovered nuclear fission in the 1930s, few imagined it would lead to weapons capable of erasing cities. The knowledge itself was neutral, but its application reshaped the world. Vacuum decay research sits at the opposite extreme. There's no application, no defense, no way to weaponize or prevent it. The only outcome of this knowledge is the weight of knowing. Does that make it irresponsible to share? Imagine a doctor diagnosing a patient with an incurable, symptomless condition that could strike at any moment. Would the diagnosis help or simply paralyze them with dread? Yet secrecy carries its own dangers. Suppressing scientific inquiry sets a dangerous precedent. What starts as withholding one unsettling theory could snowball into institutionalized censorship, eroding public trust in science. And there's another layer. If vacuum decay isn't just a hypothetical but a measurable risk, don't we have a right to know? Even if the news is grim, the truth has value. Astronomers don't stop tracking asteroids because the data might scare people. They share it because awareness, however unsettling, is the first step toward understanding. But here's the cruel twist with vacuum decay. Unlike asteroids, there's no step 2, no planetary defense system to build, no contingency plan to draft. The only preparation is existential. How do we live with the knowledge that everything could vanish before our next breath? Some argue that embracing cosmic impermanence could deepen our appreciation for existence, a sort of universal carpe diem effect. Others counter that relentless dread isn't enlightenment, it's psychological torture. Perhaps the real dilemma isn't about suppressing research, but redefining why we pursue it. Science isn't just a tool for control, it's a lens to comprehend our place in the cosmos. The terror of vacuum decay isn't in the equations, it's in our reaction to them. Maybe the question isn't should we know, but how do we stay curious in the face of the unthinkable? After all, the universe doesn't care if we panic. It simply is, and so are we for now. Not every physicist loses sleep over vacuum decay. In fact, a growing number argue the entire premise might be flawed, that the Higgs field isn't teetering on a knife's edge at all, but resting comfortably in its most stable state. Their skepticism isn't just wishful thinking, it's rooted in evolving mathematical models and fresh data from particle colliders. Picture two detectives reviewing the same evidence. One sees a ticking bomb, the other a perfectly harmless clock. Both are staring at the same equations, but their interpretations couldn't be more different. The heart of this debate lies in how we calculate the Higgs field's potential energy landscape. Early models suggested a shallow dip, a metastable state that could eventually tunnel into a lower energy valley. But newer analyses account for subtle quantum corrections and interactions with other fields that previous calculations overlooked. Think of it like surveying a hill with an outdated map. Early explorers might have missed an entire ridge that changes the slope's stability. When these additional factors are included, some simulations show the Higgs field sitting squarely at the bottom of its energy well, with no lower state to decay into. It's not a marble balanced on a ledge, it's a marble at rest in a bowl with no momentum to escape. Then there's the cosmological constant problem. If the universe's vacuum energy were truly precarious, we'd expect far more violent quantum fluctuations in empty space. Yet the cosmos appears eerily calm on large scales, with spacetime itself expanding smoothly. This observed stability hints that the vacuum might be more resilient than our doomiest predictions suggest. It's like noticing a centuries-old bridge still standing despite engineers' warnings it should have collapsed decades ago. Either we're missing something in our calculations, or the bridge is sturdier than we thought. Critics also point to the sheer longevity of the universe. 13.8 billion years is an unimaginably long stress test, plenty of time for random quantum fluctuations to trigger decay if the system were truly fragile. The fact that we're here observing galaxies and quasars from the early universe suggests the Higgs field has remarkable staying power. Of course, absence of evidence isn't evidence of absence, as scientists caution. But when your doomsday scenario requires probabilities so infinitesimal they make lottery odds look generous, it's worth questioning whether the math aligns with reality. Not all counterarguments dismiss decay entirely, some simply reframe the timescale. Even if the Higgs field is metastable, its half-life could be so astronomically long that the heat death of the universe would occur first. Imagine worrying about a dam breaking 1 trillion years after the river has dried up. This perspective shifts vacuum decay from an imminent threat to a theoretical footnote, a distant concern dwarfed by more pressing cosmic deadlines. The debate isn't just academic hair-splitting, it cuts to the core of how we model fundamental physics. Every assumption about vacuum stability relies on our incomplete understanding of quantum field theory, a framework we know breaks down at extreme energies. Some theorists propose undiscovered particles or symmetries could act as stabilizing anchors, like hidden buttresses shoring up a shaky foundation. Others speculate that gravity, often treated as a background player in these calculations, might play a decisive role in preventing decay. Until we unify quantum mechanics with general relativity, these questions will remain open. What makes this scientific tug-of-war fascinating is how it mirrors larger patterns in physics history. A century ago, physicists agonized over whether the sun could burn out overnight before nuclear fusion was understood. Later, black holes were dismissed as mathematical oddities until observational proof emerged. The Higgs stability debate might follow a similar arc, either fading as models improve or suddenly gaining urgency with new data. For now, the universe's continued existence offers a quiet rebuttal to the most alarmist predictions. But as any physicist will tell you, absence of catastrophe isn't proof of safety. It's just a very long streak of good luck. Of all the ways the universe could erase us, vacuum decay stands apart, not just for its scale but for its eerie inevitability. Most cosmic threats operate on a timetable we can measure or estimate. Asteroids, we've catalogued over 90% of the kilometer-sized ones, with deflection plans in the works. Gamma-ray bursts, these stellar death beams, are rare, and Earth would need to be directly in the firing line. Even supernovas give us warning signs as their host stars convulse in their death throes. But vacuum decay, it doesn't play by those rules. There's no countdown, no proximity requirement, no margin for error. It's the ultimate cosmic lottery where every instant is another spin of the wheel and the odds never improve. Take asteroids first. A 6-mile-wide rock like the one that doomed the dinosaurs strikes Earth roughly once every 100 million years. We can see them coming decades in advance, and projects like NASA's DART mission have already proven we can nudge them off course. The risk is real, but it's manageable, a problem of engineering and vigilance. Gamma-ray bursts are scarier, capable of sterilizing entire galaxies with their relativistic jets. But these are directional, like a sniper's bullet. Earth would need to be precisely aligned with the beam, and even then, the burst would need to occur within a few thousand light years. Statistically, you're more likely to win the Powerball jackpot while being struck by lightning. Then there's the slow death of heat decay, the universe expanding into a cold, lifeless void over trillions of years. It's the most guaranteed apocalypse of all, but so distant it might as well be abstract. Humans could theoretically outlast it by harvesting energy from black holes or hopping to younger universes. These are challenges of time and ingenuity, not instant annihilation. But vacuum decay doesn't offer the luxury of time or direction. It's not a localized disaster or a slow fade. It's a fundamental rewrite of reality's rulebook waiting in the quantum shadows. Unlike an asteroid, you can't deflect it. Unlike a gamma-ray burst, you can't hide behind a planet. And unlike heat death, it doesn't give civilizations eons to prepare. It's the only existential threat where the words "early warning system" are meaningless. By the time you detect it, the physics enabling detection no longer apply. What makes this uniquely unsettling is the role of probability. Other doomsdays follow cause and effect, a chain of events we can trace and potentially interrupt. Vacuum decay operates on pure statistics. Every second that passes without it happening doesn't make the next second safer. It's like rolling a die with a trillion sides every plank time, where one specific outcome erases the game board. The universe isn't becoming more or less stable, it's perpetually balanced on the same knife edge, moment after moment for billions of years. Yet there's a twisted comfort in this. While other catastrophes demand constant vigilance tracking space rocks, monitoring dying stars, vacuum decay absolves us of responsibility. No amount of human ingenuity can prevent it or hasten it. That liberates us to focus on the dangers we can actually influence, from climate change to nuclear war. The universe might hold an unbeatable doomsday card, but we're still playing a hand full of solvable problems. And in that balance between the inevitable and the preventable, we find the strangest gift of all, the urgency to make today matter. If humanity survives long enough to become a truly interstellar civilization, we might not just ponder vacuum decay, we could attempt to fight it. Picture a future where our descendants don't merely watch the quantum dice roll, they try to stack the deck in reality's favor. One hypothetical approach: engineering the Higgs field itself. Just as we've tamed rivers with dams and redirected lightning with rods, a sufficiently advanced civilization might seek to stabilize the universe's precarious quantum scaffolding. The tools for this cosmic renovation would dwarf anything we recognize today: particle accelerators the size of solar systems, quantum manipulators operating at energies that make the Large Hadron Collider look like a child's toy. The goal wouldn't be brute force control, but something subtler, gently nudging the Higgs field into a deeper, safer energy valley, like coaxing a marble to settle at the bottom of a bowl rather than perching on the rim. Theoretically, this could involve injecting energy or exotic matter into the vacuum itself, effectively reshaping the potential landscape of quantum fields. Imagine a team of cosmic architects reinforcing a shaky bridge, except the bridge is the fabric of space-time, and the reinforcements are phenomena we haven't even named yet. Some models suggest that concentrated dark energy or structures like cosmic strings, hypothetical one-dimensional cracks in the universe, could act as anchors, pinning the Higgs field in place. It's speculative but not impossible. After all, we already manipulate quantum states in labs today. Scaling that up to universal proportions is just an engineering problem, assuming you have a few million years to figure it out. But what if stabilization fails? Another option emerges: evacuation. Not to another planet or galaxy, those would be just as vulnerable, but to another universe entirely. Multiverse theories suggest reality might be a vast foam of bubble universes, each with different physical constants. If one bubble pops, others could remain intact. The trick is finding or creating a gateway. Wormholes, often sci-fi staples, get a second look here. While naturally occurring traversable wormholes are unlikely, a Kardashev Type 3 civilization, one harnessing the energy of entire galaxies, might attempt to construct artificial bridges between universes. The energy requirements would be absurd, but so is the alternative: sitting still and waiting for oblivion. Even wilder ideas emerge from quantum cosmology. If new universes can bud off from old ones in a process called false vacuum nucleation, an advanced society might deliberately trigger the birth of a daughter universe, one tuned for stability, then migrate into it before their original cosmos decays. Think of it as the ultimate backup plan, not just preserving data but relocating existence itself. The logistics boggle the mind, but so did spaceflight to medieval farmers. Of course, all this assumes vacuum decay is survivable at all. If the transition rewrites physics instantaneously, no warning system or escape hatch would matter. But the mere act of contemplating these scenarios changes something profound. It shifts us from passive observers of cosmic doom to active participants in reality's fate, even if that participation is purely theoretical. After all, the first step to solving a problem is believing it might be solvable, and in a universe balanced on a quantum knife edge, that belief might be the most powerful anchor of all. The chilling silence of the cosmos has long haunted astronomers. Where is everybody? This is the heart of the Fermi paradox. In a universe teeming with billions of stars and planets, why haven't we found a single trace of intelligent life? One terrifying answer might be hiding in the quantum shadows. If vacuum decay is real, it could act as the ultimate great filter, a cosmic guillotine that silently eliminates civilizations before they ever get the chance to reach across the stars. Think of the great filter as a series of hurdles life must overcome to become a galaxy-spanning civilization. Some might lie in our past. Perhaps the jump from single-celled organisms to complex life is extraordinarily rare. But the most unsettling filters could still lie ahead, lurking like traps on the path to interstellar maturity. Vacuum decay fits this nightmare scenario perfectly. It wouldn't just wipe out a civilization. It would erase the very physics that civilization relies on, resetting the universe like a corrupted computer file. No ruins, no radio signals, no Dyson spheres, just an infinite void where intelligence briefly flickered before being permanently deleted. This idea reshapes how we interpret the cosmic silence. Most great filter candidates, nuclear war, climate collapse, rogue AI, are localized threats. A civilization could succumb while others thrive elsewhere. But vacuum decay is different. It doesn't discriminate. A single quantum fluctuation anywhere in the universe could trigger a chain reaction that engulfs everything. If this is the true filter, it would explain why the cosmos feels so empty. Entire galactic empires might have risen and fallen, only to vanish without a trace when their quantum luck ran out. The universe wouldn't just be a graveyard, it would be a chalkboard wiped clean before the next equation could be written. There's a grim elegance to this explanation. Unlike theories invoking self-destruction or resource exhaustion, vacuum decay doesn't require aliens to make mistakes. They wouldn't need to trigger it through war or recklessness. The universe itself would be the executioner, striking at random with no warning and no recourse. Even a hyper-advanced civilization, capable of harnessing black holes or bending spacetime, would be powerless against the rewriting of physical laws. The filter isn't something you can outsmart or outrun. It's the ultimate checkmate, but here's the twist. If vacuum decay is the great filter, our very existence becomes a statistical miracle. The fact that we're here pondering this question suggests our cosmic bubble has lasted longer than most, long enough for life to evolve against astronomical odds. Perhaps we're among the first life forms in our universe to reach this stage, teetering on the edge of a silent abyss. Or perhaps, against all probability, the Higgs field is more stable than we fear and the filter lies elsewhere. Either way, the silence of the cosmos suddenly feels far more ominous. Every quiet radio telescope isn't just an absence of signals, it's a question mark hanging over the fragility of existence itself. This isn't just about aliens, it's about us. If vacuum decay is the universe's silent killer, then humanity's window of opportunity might be narrower than we thought. The stars beckon, but the clock could be ticking on a scale we can't even perceive. The cosmic dice have rolled in our favor so far, but the game isn't over. And the next roll could be the last. So should you cancel your weekend plans over vacuum decay? Let's be brutally honest. If a true vacuum bubble forms tonight, your dinner reservation will be the least of anyone's concerns. By the time your brain could process the words "check please," the very concept of restaurants or brains or money might no longer exist. Poof, not with a bang, not with a whimper, but with a silent cosmic shrug. That's the darkly liberating truth about this particular doomsday scenario. It's the ultimate out-of-office message. No survival bunker, no asteroid deflection plan, no last-minute rocket to Mars would make the slightest difference. The universe doesn't send RSVP. There's a twisted humor in this helplessness. Most existential threats come with nagging what-ifs, or what if we'd prepared better, what if we'd heeded the warning. Vacuum decay laughs at those anxieties. It's the one disaster where fretting is as pointless as ignoring it. Either the quantum dice land wrong tomorrow, ending everything before your morning coffee cools, or they don't, and you've spent years agonizing over a statistical phantom. The irony, worrying about it consumes more of your finite existence than the event itself ever could. This isn't nihilism, it's perspective. The same physics that makes vacuum decay possible also ensures your favorite song still sounds the same today as it did yesterday. Gravity hasn't forgotten to keep your feet on the ground. The sun hasn't misplaced the recipe for nuclear fusion. For all its terrifying potential, the Higgs field has been a model cosmic citizen for 13 billion years. Statistically, you're more likely to be struck by lightning while adopting a pet tornado than to witness reality unravel. So go ahead and plant that tree, book that trip, learn that instrument. Not because vacuum decay isn't real, but because living as if it's imminent is like refusing to sleep for fear you'll stop breathing. The universe's fragility isn't a reason to freeze. It's a reminder that stability was never guaranteed in the first place. Every mundane, wonderful moment you experience is already beating astronomical odds. The meeting's at 3, the laundry's piling up, and the universe is still here. Might as well act like it. There's something strangely clarifying about staring into the abyss of total annihilation. Vacuum decay doesn't just threaten lives, it threatens meaning itself. If the universe can rewrite its own rules without notice, what happens to the monuments we build, the art we create, the love we nurture? Philosophers have wrestled with impermanence for millennia, but quantum physics adds a brutal twist. Our expiration date isn't just uncertain, it could arrive before this sentence ends. Some might argue this renders human ambition absurd. Why cure diseases, compose symphonies, or explore the stars if every achievement could vanish mid-celebration? It's the ultimate cosmic joke. We're ants constructing sandcastles on the shore, knowing the tide isn't just coming, it could erase the ocean. The ancient Stoics advised accepting what we cannot control, but even they never imagined a scenario where reality itself might rescind the terms of existence. Yet there's another way to see it. The very fragility of our universe might be what makes our actions matter more, not less. Consider a firefly glowing in a vast, dark forest. Its light is brief and tiny against the enormity of the night, but that's precisely what makes it beautiful. If we knew the cosmos would endure unchanged for eternity, our works might feel like graffiti on an indestructible monument. But if existence is a flickering candle in the quantum wind, then every act of kindness, every leap of curiosity, every moment of connection becomes a defiance of the void. History's greatest creators often worked under the shadow of mortality. Mozart composed with tuberculosis creeping in, Frida Kahlo painted through chronic pain, and astronauts like Kalpana Chawla reached for the stars knowing the risks. Their urgency wasn't born from infinite time, but the lack of it. Vacuum decay simply scales this truth to cosmic proportions. The difference between someday and now isn't just practical, it's existential. This isn't about doom-scrolling the universe's expiration date. It's about recognizing that meaning was never in the permanence of things, but in their happening at all. The particles in your body have existed for billions of years, but their arrangement, the miracle of you, is staggeringly unlikely and breathtakingly temporary. Whether the universe lasts another trillion years or collapses tonight, this moment where stardust became conscious enough to ponder its own fragility is the marvel. So build your sandcastles. The tide may spare them or it may not, but the act of building is the only answer the abyss will ever get. Right now, beneath the Franco-Swiss border, scientists are scrutinizing the Higgs boson with a precision that would make a watchmaker blush. CERN's Large Hadron Collider isn't just recreating Big Bang conditions, it's running quantum diagnostics on reality itself. Every proton smash unveils new data about the Higgs field's behavior, probing whether this cosmic scaffold is solid steel or spinning glass. These experiments might sound like abstract puzzles, but there's nothing academic about the stakes. Confirming the field's stability could mean the difference between a universe built to last and one playing Russian roulette with quantum triggers. Recent upgrades to the LHC's detectors allow measurements accurate to 1 part in a billion, like weighing a single snowflake in a blizzard. One groundbreaking 2023 study analyzed Higgs boson interactions with top quarks, the heaviest known particles. Think of it like stress testing a bridge by driving increasingly heavy trucks across it. The results so far, the bridge holds, but the team also found the Higgs field's potential energy curve is shallower than early models predicted, meaning the drop to a lower state, if it exists, might be less steep than feared. It's like discovering the marble balanced on your salad bowl is slightly stickier than you thought. This research isn't confined to underground tunnels. Space telescopes like Hubble and JWST contribute by observing the universe's large-scale structure. If vacuum decay had already transformed distant regions, we'd expect bizarre gravitational lensing patterns or sudden voids where physics behaves oddly. So far, the cosmos looks uniformly stable, no phantom zones where light bends wrong or galaxies move impossibly. It's a silent reassurance written across billions of light years. Meanwhile, quantum theorists are rewriting the playbook. New calculations incorporating gravitational effects suggest spacetime itself might act as a stabilizer, subtly warping the Higgs field's energy landscape like a weighted blanket over a restless sleeper. Other models propose undiscovered particles that could anchor the field, hypothetical heavier siblings to the Higgs that haven't shown up in colliders yet. It's detective work where every clue either inches us toward safety or confirms we're living on borrowed time. What makes this more than theoretical noodling is the sheer scale of consequence. Most scientific debates simmer in academia for decades before touching public consciousness. This one whispers about rewriting reality itself. When researchers argue over the Higgs field's half-life, they're not splitting hairs, they're estimating how many dice rolls the universe gets before snake eyes. And while the current odds look reassuring, a 1% chance over 10 to the 100th power years, that's not zero. The most profound insight emerging from these labs isn't about doom but humility. Every particle collision underscores how little we truly control. We can map quantum fields with astonishing precision, yet remain passengers in a cosmos where the rules could change without notice. That tension between understanding and powerlessness might be the defining paradox of our scientific age. The Higgs field doesn't care if we watch it. But by watching, we glimpse either an eternal foundation or a countdown we can't stop. The sheer scale of vacuum decay forces us to confront two opposing truths: that reality is unimaginably fragile yet staggeringly resilient. Our universe has balanced on this quantum knife edge for billions of years, every second a silent defiance of statistical oblivion. It's humbling to realize that the stars we see at night, the ground beneath our feet, even the laws of physics themselves exist not by necessity but by precarious cosmic consent. One random quantum flicker could erase it all in less time than it takes for a synapse to fire. But here's the paradox: that fragility is what makes existence extraordinary. Every sunrise, every breath, every whispered "I love you" persists against unfathomable odds. We're living in a universe that shouldn't, by all mathematical rights, still be here. The fact that we can ponder its demise is itself a miracle. Think of reality as a soap bubble, its iridescent surface trembling in the void. It could pop at any moment. Yet for now, it holds reflecting galaxies and symphonies and first kisses in its fleeting film. So let's end with a question that's equal parts terrifying and liberating. What if today were the last day of physics as we know it? Not in some distant future, but now before you finish watching this video. Would you rage against the dying of the light, or would you marvel that there was light at all? Maybe you'd call someone you've been meaning to forgive, finally write that novel, or just sit quietly under a tree, feeling the wind one last time. The true power of this thought experiment isn't about fear, it's about focus. Vacuum decay reminds us that the universe owes us nothing. Every moment is stolen time, a temporary alignment of quantum dice that lets us experience everything. So look up tonight. The stars you see might be long gone, their light a postcard from the past, or they might vanish tomorrow, rewritten into something unknowable. But tonight they're here, and so are you. That's enough.